Welcome back to Tech Unplugged, everybody. We have something really cool cooking. We're kicking off a whole new series all about databases.
Yep, this is our first deep dive, and we're going straight to the heart of it with PostgreSQL.
I love it. PostgreSQL. Now, we know databases can seem kind of, well, intimidating. But the truth is, they're the backbone of so much of the tech we use every day.
Absolutely. So we're going to break it all down, what a database is, why it even matters, and what makes PostgreSQL so special. No jargon, just the good stuff.
Exactly. Think of it as your cheat sheet to the world of databases. So let's start with the basics. What exactly is a database?
You can picture a database like a really well-organized digital filing cabinet, but instead of papers, it holds tons of information, and it's designed to make finding, updating, and managing all that data super efficient.
A digital filing cabinet. I like that. But why should our listeners, the people out there in podcast land, care about these digital filing cabinets?
Oh, they're crucial. I mean, almost every app you use, every website you visit, there's a database working behind the scenes.
So whether you're saving your settings in your favorite game or buying something online, it's all powered by a database.
Pretty much. They handle everything from the simple stuff to the crazy complex stuff, managing huge amounts of data and millions of transactions constantly.
And when it comes to cost, that's where PostgreSQL really comes into its own.
Because it's open source, right?
Exactly. Open source means it's free to use. That's a huge advantage, especially if you're a startup or just trying to be mindful of your budget.
Free is always good.
Mm.
Okay, so we've established they're important and can be budget friendly. But I've got a feeling there's not just one type of database out there. It's more like a whole family, right?
You got it. To paint a clearer picture, there are a few main categories. First up, you've got your relational databases, like our friend PostgreSQL.
Relational databases. Okay. What's the deal with those?
So they organize data into tables, think rows and columns, and those tables have defined relationships with each other.
Okay, so it's all about structure. Structure is key. And they use a standard language called SQL to interact with all that data. Relational databases are famous for their reliability, often described by what are called ACID properties.
ACD property sounds a bit technical. What does that even mean?
Think of AC-tree properties like guarantees for your data. They make sure that transactions are processed reliably and consistently.
So it's a promise that your data is safe and sound.
Pretty much. Then you've got your object-oriented databases. They store data as objects, which are these self-contained units of information.
Okay, objects a bit different from the table structure then.
Yeah, a different approach. And then there's NoSQL, another big category. NoSQL is designed to be super flexible and scalable, especially for data that doesn't fit neatly into those rows and columns.
Interesting. So NoSQL is for when you need to break free from the traditional table structure.
Exactly. It handles things like documents, key-value pairs, or even data represented as graphs.
Graph databases, now those sound particularly fascinating. When would you use one of those?
Graphs are perfect when the relationships between data points are just as important as the data itself.
So not just what the data is, but how it's connected.
Exactly. Think of social networks where knowing who's connected to whom is key, or recommendation systems that suggest products based on what other users have liked.
Ah, that makes sense. So different tools for different kinds of data. You also mentioned time series databases earlier. What are they good for?
Time series databases are optimized for data that's collected over time with timestamps. They're great for tracking financial markets, monitoring sensor readings from the Internet of Things, or analyzing web traffic patterns.
So if your data is all about change over time, a time series database is the way to go. Now, you said earlier that relational databases like our star PostgreSQL have been kind of the top dog for a while. What makes them so enduring?
Their strength lies in their proven reliability and the sheer power of SQL. That structure we talked about and those ACID properties, they make relational databases the go-to choice for anything where data accuracy is absolutely mission critical.
Okay, so that brings us back to PostgreSQL. It's not exactly a new kid on the block, right? What's the backstory there?
Nope, it's got a long history going all the way back to 1986. It actually started as a research project called PostgreSQL itself, a successor to an even earlier database called Ingress.
So it's got a real lineage.
It does. A major turning point came in '94 when they added support for SQL, which really expanded its appeal. Then in '96, it officially became PostgreSQL and has been under constant development ever since.
Wow, constant development for almost 30 years. That's some serious dedication. So what are some of the big reasons why PostgreSQL is such a popular choice today?
Well, first off, that open source nature we mentioned, it's free and has a huge community of developers and users who are constantly improving it and providing support.
So it's like a global team effort.
Exactly. It's also known as an object relational database. That means it takes the best of both worlds, combining the strength of traditional relational databases with some of the more advanced features you find in object-oriented systems.
Object relational, so it can handle the structured stuff, but also more complex data types.
Exactly. And then there's its extensibility. You can really customize PostgreSQL to fit your needs, defining your own data types, functions, the works.
So it's like a database that you can tailor to your specific project.
Exactly. And it plays well with a ton of different programming languages, not just its own PLPG SQL, but also things like Perl, Ruby, Python, Java.
Wow, that's flexible. But what about when you've got tons of data to crunch? How does PostgreSQL actually perform?
It's got some serious performance jobs. It uses sophisticated indexing, which basically means it can find data super fast without having to search through everything.
So it's like having an index in a book. You can jump straight to what you need.
Exactly that. And it can run queries in parallel, using multiple processors to get things done even quicker. For certain operations, it even does something called just-in-time compilation, which optimizes queries on the fly.
That's some smart stuff. What about the types of data you can store in PostgreSQL? Is it just numbers and text, or can it handle more?
Oh, it goes way beyond the basics. You can store network addresses, geometric shapes for things like maps, JSON data, which is really common in web apps, arrays, and even your own custom data types if you need something unique.
From simple numbers to complex data structures, pretty impressive. Now, what happens when you've got lots of users or applications trying to access the database all at the same time? How does PostgreSQL handle all that traffic?
That's where concurrency control comes in. PostgreSQL uses something called multi-version concurrency control, or MVCC for short.
MVCC, another acronym, what does that one do?
Imagine it takes snapshots of the data at different points in time. This allows lots of users to read and write data at the same time without stepping on each other's toes.
So it's like a database time machine keeping everything in sync.
In a way, yeah. This means readers don't have to wait for writers, and writers don't block readers. It's all about smooth sailing.
MVCC, definitely a mouthful, but it sounds like a pretty clever solution. Now, these days, keeping data safe and always accessible is super important. What does PostgreSQL offer in terms of security and high availability?
It's got you covered. For high availability, it supports various types of replications, so you can have backup servers that are ready to take over if the main one goes down.
So if one server goes kaput, another one steps in to save the day.
Exactly. And for security, it offers things like SSL encryption to protect data as it travels over the network, granular control over who can access what data, and strong authentication methods to verify user identities.
So it's all about layers of protection.
Yep, keeping your data safe and sound. And to top it off, it sticks closely to SQL standards, which is great for compatibility. And it's designed to scale, so it can handle massive amounts of data and tons of users without breaking a sweat.
Scalability is a big deal these days. Okay, so now that we've covered the high-level stuff, let's dive into some of the fundamental concepts behind how PostgreSQL works. First up, how is the data actually organized and structured within the database?
At its core, PostgreSQL, as a relational database, uses the relational model. That means your data is organized into tables, like those spreadsheets you might be familiar with.
Okay, tables, rows, and columns.
Precisely. Each row in a table represents a single record, like a customer or a product. Each column represents a specific attribute of that record, like the customer's name or the product's price. And to link related information across different tables, we use primary keys and foreign keys.
Primary and foreign keys, they sound important. What are those all about?
Think of a primary key as a unique ID for each row in a table. It's like a social security number for your data, making sure each record is distinct. A foreign key is a reference to a primary key in another table. It's how we create relationships between tables, connecting the dots.
So primary keys identify and foreign keys connect. What are the big advantages of this whole relational model approach?
It's really powerful. First, it's simple and flexible, mirroring how we think about things in the real world. Second, it lets you query and manipulate data in incredibly sophisticated ways using SQL. And of course, there are those ACIA properties we talked about, ensuring your data stays consistent and reliable.
Got it. So we've got this structure of tables, rows, and columns all linked together. Now, when we're talking about the overall design of a PostgreSQL database, we often hear the terms schema and instance. What's the difference?
Imagine the schema as the blueprint of your database. It's the plan that defines all the objects in it, the tables, the columns, the relationships, everything.
The schema is the plan.
Okay, what about the instance?
The instance is the actual living, breathing PostgreSQL server. It's the process running on your computer that stores and manages the data based on that schema blueprint.
So the schema is the idea, and the instance is the real-world implementation.
You got it. And you can even have multiple schemas within a single instance. It's like having different sets of blueprints for different parts of your data. Okay, so we have the blueprint and the building. Now, to actually create and manage these schemas and work with the data, we use different languages, right? DDL, DML, and DCL. What are those all about?
Exactly. They're like specialized tools for different database tasks. DDL, or Data Definition Language, is all about defining and managing the structure of the database.
So you want to create a new table or modify an existing one, you use DDL.
Yep. The key commands are create for making new stuff, alter for changing existing things, drop for getting rid of stuff entirely, and truncate for wiping the data from a table while keeping the table itself.
Create, alter, drop, truncate, got it. What about actually putting data into those tables and getting it back out? That's where DML comes in.
Right. DML stands for Data Manipulation Language, and it's all about working with the data itself. You use select to retrieve data, insert to add new records, update to modify existing ones, and delete to remove records.
Okay, so DDL is for the structure and DML is for the data. What about that last one, DCL?
DCL is Data Control Language, and it's all about security and permissions. It's used to control who has access to what data and what they can do with it.
So it's like the bouncer at the database club deciding who gets in and what they're allowed to do.
That's a great way to put it. DCL is all about making sure the right people have the right access and no one else.
Security is super important. Now let's talk about keeping our data organized and avoiding unnecessary duplication. That's where normalization comes into play, right?
Exactly. Normalization is a set of guidelines for designing your database schema to minimize redundancy and improve data integrity. It's about making sure the same information isn't stored in multiple places, which can lead to inconsistencies and errors.
So it's like streamlining your data, making sure everything has its place.
Absolutely. We often talk about different normal forms, 1NF, 2NF, 3NF, and so on, which are like levels of normalization.
Okay, normal forms like levels in a game. What
Yeah.
do these different levels mean?
First normal form, or 1NF, is the most basic. It says each column in a table should only contain atomic values, meaning you can't have multiple pieces of information crammed into a single cell. It also prohibits repeating groups of columns.
So one piece of information per cell and no redundant groups of columns.
Exactly. Second normal form, or 2NF, builds on 1NF. It says all the non-key attributes in a table should be fully dependent on the entire primary key.
Fully dependent.
It means if an attribute only depends on part of a composite primary key, it should be moved to a different table. Third normal form, or 3NF, goes even further, saying there shouldn't be any transitive dependencies.
Transitive dependencies, that sounds complicated. What does that mean?
It means a non-key attribute shouldn't depend on another non-key attribute. It should only depend directly on the primary key. Normalization might seem a bit abstract at first, but it's really about making sure your data tells a clear and consistent story. By avoiding repetition, you ensure that when something changes, you only need to update it in one place.
It's all about data integrity, keeping things clean and accurate. Could you give us a real-world example of how normalization might look in practice?
Sure. Imagine an e-commerce site that sells products. You could have a products table to store information about each product, like its ID, name, description, and price. Then you could have an orders table to store information about each order, like the order ID, the customer who placed the order, and the order date. And finally, you'd have an order items table to link the orders and products, specifying which products are included in each order and the quantities.
So instead of repeating product information for every order, you have a separate table to manage those relationships.
Exactly. That way, if the price of a product changes, you only need to update it in the products table, and the change is automatically reflected in all related orders.
That's clever. It keeps things organized and prevents a lot of potential headaches. Now let's talk about making sure the data entered into our database is actually valid and makes sense. That sounds like the role of data integrity and constraints.
You got it. Data integrity is all about ensuring your data is accurate and reliable throughout its entire life cycle in the database. Constraints are the rules we set up to enforce this integrity.
So constraints are like the quality control for our data.
Exactly. Common constraints in PostgreSQL include things like primary key, which ensures that each row in a table has a unique identifier. Foreign key, which maintains those relationships between tables. Unique, which enforces that certain values in a column are unique across all rows. Not null, which ensures that a column always has a value. And check constraints, which let you define custom rules for what data is allowed in a column.
So constraints are like the bouncer and the quality control combined. Can you give us an example of how a constraint might work in practice?
Sure. Let's say you have that orders table with a customered column linking to your customers table. You would use a foreign key constraint to make sure every customer in an order actually refers to a real customer in your customers table.
So it prevents you from creating an order for a customer that doesn't exist.
Exactly. You can even do things like specifying what should happen if a customer record is deleted. With the on-delete cascade option, if you delete a customer, all their associated orders would also be deleted automatically.
Wow, that's powerful. But it sounds like something you'd want to use carefully. Okay, so we have our data structured and we have rules in place to keep it clean. But what about actually making the database perform well, especially when we have huge amounts of data? That brings us to indexing.
Indexing is crucial for performance. Think of it like the index in a book. It lets you jump straight to the information you need without having to read the whole thing. In a database, an index allows PostgreSQL to find specific rows in a table super fast without scanning the entire table.
So indexes are like shortcuts for finding data.
Exactly. The most common type is the B-tree index, which is great for finding data based on equality or ranges. For example, if you often search for customers by last name, a B-tree index on the last name column would make those searches blazing fast.
B-tree index. Got it. Are there other types of indexes?
Yep. There are hash indexes, which are great for equality comparisons, but not so much for ranges. And then there are more specialized types like GIST and GIN for more complex data types.
So different indexes for different needs. How do you actually create an index in PostgreSQL?
It's pretty straightforward. You use the create index command, give your index a name, specify the table and the column you want to index. That's all there is to it.
Simple enough. Okay, let's shift gears a bit and talk about the underlying infrastructure that supports PostgreSQL. We often hear about configuration files and all sorts of parameters. What are some of the key things our listeners should know about this side of things?
The heart of PostgreSQL's configuration lives in a file usually called postgresql.conf. This file is packed with settings that control how the database server behaves.
So that's like the control panel for the entire database.
Exactly. Some of the key parameters you'll likely encounter include listen addresses, which determines which network interfaces PostgreSQL will listen on for incoming connections.
So which doors it keeps open for communication.
Exactly. Then you've got port, which sets the default port number, usually 5432, and max connections, which limits how many simultaneous connections the server will allow. It's important to think about how much traffic you expect and adjust this accordingly.
So these are like the high-level settings for how the server operates. Are there also settings that specifically affect performance?
Oh, absolutely. There are parameters like shared buffers, which controls how much memory PostgreSQL uses to cache frequently accessed data. A larger value here can make a huge difference for read-heavy workloads.
So it's like giving the database a bigger brain to remember things?
You could think of it that way. Then there's workmem, which sets how much memory each individual query operation can use for things like sorting and hashing.
So giving each task enough room to work efficiently.
Exactly. And the write-ahead logging settings are critical for both performance and making sure your data is safe.
Write-ahead logging, what's that?
Think of it like a detailed journal that records every change to the database. This is crucial for recovering from crashes or errors.
Ah, so it's like a safety net for your data.
Precisely. The setting wall level controls how much detail gets written to this journal, and Maxwell Cinders sets how many connections can be used for replicating the database to other servers.
So lots of knobs and dials to fine-tune how PostgreSQL handles data and transactions. Speaking of safety nets, what about backing up and recovering our precious data in PostgreSQL? What are the main approaches?
Backing up your data is absolutely critical. PostgreSQL gives you a few different ways to do it. Logical backups create a sort of blueprint of your database in the form of SQL scripts. Physical backups, on the other hand, make a direct copy of the database files.
So logical is like the instructions and physical is like cloning the whole thing.
That's a great analogy. And by enabling continuous archiving of those write-ahead logs we talked about, you get something called point-in-time recovery, or PITR.
PITR, okay. What's the advantage of that?
With PITR, you can rewind your database to any specific point in time. Super useful for recovering from accidents or mistakes.
Wow, that's like a time machine for your data. How does continuous archiving make that possible?
It constantly writes a log of every single transaction to a series of files. By keeping these files safe, you have a complete history of everything that happened to the database.
So if something goes wrong, you can go back in time and fix it.
Exactly. Okay, so we have our PostgreSQL system up and running. We're backing up our data like responsible adults. What about keeping an eye on things and making sure everything is running smoothly?
Monitoring and maintenance, that sounds like the responsible thing to do. What tools and strategies do we have in PostgreSQL?
PostgreSQL comes with some great built-in tools. Explain Analyze shows you exactly how a query is executed, helping you identify bottlenecks. The PG Stat Statements extension lets you track the performance of all your queries.
So it's like having a performance profiler for your database.
You got it. And standard system monitoring tools like pgtop or htop, along with checking the logs, can tell you how your resources are being used.
So keeping an eye on the vital signs. What about routine maintenance?
Regular maintenance is key. You'll want to run VCUM to clean up disk space, Analyze EE to update statistics that help the database run efficiently, and potentially rebuild indexes from time to time.
Keeping things tidy and optimized.
Exactly. And of course, always keep your PostgreSQL installation up to date with the latest security patches and minor version updates.
Security and stability, can't forget those. Now, earlier you mentioned replication as a way to achieve high availability. Can you walk us through how that works in PostgreSQL?
Sure. PostgreSQL offers two main flavors of replication: physical and logical. Physical replication creates an exact, real-time copy of your entire database on another server.
So it's like mirroring the whole database.
Exactly. This is great for having a hot standby server that can take over instantly if the main server fails.
Like a backup quarterback ready to step in.
Perfect analogy. A key setting here is hot standby feedback, which helps prevent conflicts between the primary and standby servers.
So keeping the backups in sync.
Mhm.
What about logical replication? How's that different?
Logical replication is more about sharing specific data rather than mirroring the entire database.
So picking and choosing what to replicate.
Exactly. You define what data you want to share on the source database, and then on the target database, you create a subscription to receive those updates.
Like subscribing to a data feed.
Exactly. This can even work between different versions of PostgreSQL, which is super useful for complex setups.
That's flexible. Now, what happens when you have truly massive tables with billions of rows? How do you manage those beasts?
That's where partitioning comes in. Partitioning is about breaking down those mega tables into smaller, more manageable pieces.
So dividing and conquering.
You got it. This speeds up queries because PostgreSQL only needs to search the relevant partitions, not the whole table. It also makes things like backups and maintenance much easier.
Makes sense. How do you actually partition a table?
You can partition based on things like date ranges, value ranges, or lists of values. PostgreSQL has built-in partitioning features, and there are extensions like pgpartman that can automate the whole process.
So breaking down those giants into bite-sized chunks. Now, what about when you have a huge number of applications all trying to connect to your database at once? How do you handle that kind of traffic jam?
That's where connection pooling comes in handy. Instead of creating a new connection every time an application needs to talk to the database, a connection pooler keeps a bunch of connections open and ready to go.
So it's like having a pool of taxis waiting at the airport instead of calling a new one every time you need a ride.
Exactly. This can drastically improve performance when you have lots of applications trying to access the database.
Reusable connections, a very efficient approach. What about spreading the workload across multiple database servers? Is that what load balancing is all about?
Yep, load balancing is all about distributing the work. In PostgreSQL, this is often used to spread read-heavy workloads across multiple servers, taking the pressure off the main database server.
So sharing the load for better performance.
Exactly. Connection poolers can also play a role in distributing this traffic.
Teamwork makes the dream work. And to make sure our application stays up and running, even if a server crashes, we need high availability, right?
Absolutely. A common approach is to use a primary replica setup. You have one main server and one or more standby servers that are kept up to date. If the main server goes down, a standby can take over seamlessly.
So it's like having an understudy ready to go on stage if the lead actor gets sick.
Precisely. Tools like Patroni can automate this whole failover process.
Automated failover, that's reassuring.
Yeah.
Okay, let's talk a bit about managing where our PostgreSQL data actually lives on disk. That's where table spaces come in, right?
Yep. Table spaces let you choose where PostgreSQL stores its files. This can be useful for distributing data across multiple disks for better performance or for managing storage across different volumes.
So it's about having more control over where the data physically resides. How do you actually work with table spaces?
You create them with the create tablespace command, specifying the location on your system. You can even move entire databases to a different tablespace using alter database, set tablespace.
So it's about flexibility in data storage. Finally, when we're thinking about scaling our PostgreSQL setup to handle massive amounts of data and traffic, what are some of the common architectural patterns we might see?
There are tons of options depending on your specific needs. For many applications, a single, well-equipped server can be surprisingly powerful and cost-effective.
So start simple and scale up as needed.
Exactly. In the cloud, you might use network-attached storage like EBS. As your read traffic grows, you can add read replicas to show the load.
Divide and conquer again.
Yep. Some cloud providers even offer managed database services like Aurora, which can simplify things but come with their own considerations.
Managed services, sometimes convenience comes at a cost.
True. For more demanding write workloads, you might explore active-active setups where multiple servers handle writes, but these can get complex.
Multiple writers sounds like a recipe for potential conflicts.
It can be tricky. Then there's sharding, where you distribute data across multiple servers. This can be very effective, but often requires some careful planning.
Breaking the data into smaller pieces and spreading it around.
Exactly. And finally, there are distributed key value stores with SQL interfaces, which offer both scalability and resilience.
Lots of different options to choose from. It's great to see PostgreSQL being used in so many different ways. Can you give us some real-world examples of companies or applications that rely on PostgreSQL?
Oh, tons. Instagram, for example, uses PostgreSQL to manage its massive user base and all those likes and comments.
So PostgreSQL is powering our social media addictions.
In a way, yes. Crunchy Data Warehouse is built on PostgreSQL, providing a data warehousing solution that leverages all of its strengths. PostgreSQL is also popular in data engineering pipelines for building and managing data warehouses.
From social media to data warehousing, quite a range.
It is. Even popular platforms like WordPress can use PostgreSQL as their backend database. And a rapidly growing area is using PostgreSQL for managing vector embeddings, which are crucial for things like similarity search and AI applications.
So PostgreSQL is even powering the AI revolution.
In some ways, yes, and it's incredibly versatile. You can even connect it to other database systems like MongoDB, allowing you to work with data from multiple sources seamlessly.
That's powerful. Now, what happens when your PostgreSQL database starts to slow down? What are some of the go-to optimization techniques?
There are a few key things to look at. First, you want to identify any slow queries. The pgstat statements extension can help with that.
Find the bottlenecks.
Exactly. Once you know which queries are causing trouble, adding indexes can make a huge difference.
Those shortcuts again.
Yep. You also want to choose the right type of index for your needs. B-trees are a good default, but hash indexes might be better for certain situations.
So tailor the index to the task.
Right. Tuning those configuration parameters we talked about earlier can also make a big difference.
Tweaking the settings under the hood.
Yep. And Explain Analyze I can help you understand exactly how PostgreSQL is executing your queries so you can spot inefficiencies.
Getting under the hood and seeing what's going on.
Exactly. You can also use views and materialized views to pre-calculate or aggregate data, which can speed things up considerably. And for massive data sets, partitioning can be a lifesaver.
Breaking it down into smaller pieces. Again.
Yep. And of course, make sure you have proper connection pooling in place to avoid performance bottlenecks from too many connections.
So lots of ways to squeeze more performance out of PostgreSQL. Now, data security is always a top concern these days. What are the essential things to consider when it comes to PostgreSQL security?
Security is paramount. Enabling SSL encryption is a must to protect data as it travels over the network.
Encrypting the data in transit.
Exactly. Strong passwords and robust authentication mechanisms are crucial.
Keeping the bad guys out, right?
The pghba.conf file is your control center for who's allowed to connect to the database.
The database's guest list.
You could say that. And PostgreSQL offers fine-grained access control with row-level and column-level security, allowing you to control exactly who can see and modify specific data.
So it's like setting up very specific permissions for each piece of data.
Precisely. While PostgreSQL doesn't have built-in encryption for data at rest, you can implement that at the operating system or file system level.
Keeping the data safe even when it's just sitting there on disk.
Exactly. Now, the world of databases is always evolving. What are some of the emerging trends or cool new extensions in the PostgreSQL ecosystem?
I'm all ears.
One exciting area is the PG vector extension, which lets you store and search vector embeddings, a key technology for AI and machine learning.
So PostgreSQL is getting into the AI game.
Big time. Then there are extensions like PG Parquet and PG Incremental that make it easier to work with data stored in the popular Parquet format, often used in data lakes.
Connecting PostgreSQL to the wider world of data.
Yep. And the integration with large language models, or LLMs, is getting really interesting. There are extensions that let you use LLMs directly from PostgreSQL for things like analyzing text or generating those vector embeddings.
So PostgreSQL can even tap into the power of AI. That's amazing. Finally, PostgreSQL is open source, meaning anyone can contribute to its development. What does that process look like? I'm curious about that.
It's a community effort. Even if you're not a programmer, you can contribute by improving the documentation, testing new features, or helping other users.
So there's a role for everyone.
Exactly. For code contributions, the main hub is a mailing list called PGS Quail Hackers. You submit your code changes or new feature ideas there for discussion and review.
So it's a collaborative process.
Very much so. And for a code change to be officially included, it needs to be reviewed and approved by one of the project's committers.
A system of checks and balances. Well, we have covered a ton of ground in this deep dive into PostgreSQL. I feel like I've learned so much.
Me too. We've really only scratched